This is the 4.2 video on the mean value theorem. The mean value theorem says that if f is continuous on the closed interval AB and differentiable on the open interval AB, and there exists a number C in AB such that f of B minus f of A equals over B minus A equals f prime of C. It's very important. It has to be continuous on the closed and differentiable on the open. This is what we call, last year it was a goat. I think I want it to be a sheep again. Only he's mean. Let's give him some eyebrows. He's mean. He's the mean value goat. Sheep. F prime of C equals f of B minus f of A over B minus A. This is for Ba. It's the mean value goat. He's the mean value theorem. Whoops, not MTV. Not MTV. MVT. We call it the MVT. And that's acceptable. You can, if it asks for the mean value theorem on the AP exam, you can put MVT and that is fine. What that means, do I want to read all this? Yes. Just like the intermediate value theorem, this is an existence theorem. The mean value theorem does not tell you what the value of C is, nor does it tell you how many may exist. You must keep in mind C is an X value. Also, the hypothesis of the mean value theorem is highly important. If any of the part of the hypothesis does not hold, the theorem cannot be applied. That's important. Basically, the mean value theorem says that the average rate of change, oops, I'm writing with that, is f of B minus f of A over B minus A equals the instantaneous rate of change, f prime of C, at some point in the interval. Graphically, what that means is, ooh, it's a Superman arrow. It's red and blue. If you find the secant line, if you draw a line connecting A and B, and find the slope of this line, f of B minus f of A over B minus A, and then somewhere on this graph, okay, the tangent line has to be parallel. So the derivative of the tangent, the slope of the tangent line, must equal the slope of the secant line somewhere in the interval. And to find it, we're just going to use the mean value theorem. Example 1, a plane begins its takeoff at 2 p.m. on a 2,500 mile flight. The plane arrives at its destination at 7:30 p.m. Ignore time zone changes. Explain why there were at least 2 times during the flight when the speed of the plane was 500 miles an hour. Well, this is the instantaneous rate of change. Let's call it f prime of C. And that's miles per hour. I've got to sneeze. It's like it's coming and it's going to go away and then I'm going to be stuffy. Cry. The plane arrives at its destination at 7:30 p.m. So if you do 7:30, it took off at 2 o'clock. So how many hours was it in the air? Well, would you believe 5.5 hours? That should make sense. And it went 2,500 miles. So 2,500, he went 2,500 miles in 5.5 hours. If you stick that in your calculator, you will get 454.545. Well, explain why there were at least 2 times during the flight when the speed of the plane was 400 miles an hour. Well, think about the plane. When he takes off, he flies and then he comes back down and he stops. Here he is again. Okay. He takes off. His speed is 0 when he starts. And then he gets up to 454.545 somewhere, at least. And then he comes back down and he's 0. So what had to have happened at least 2 times? It had to start and stop at 0, so it had to pass through 450 twice. I don't know why I'm writing twice. Yeah. So you would say they explain why because of the mean value theorem that says that the average, this is his average speed. The average speed has to equal the instantaneous rate of change at least once. So he had to have got up to 54.545, and therefore he had to pass through 400 at least twice. All right, let's actually use the question. It says, what? Use a question? I don't know what that meant. Apply the mean value theorem to the function on the indicated interval in each case to make sure the hypothesis is true. Then find all values of C in the interval that are guaranteed. First of all, is this continuous? Well, it's just a polynomial, so yes, it's continuous. So this is f of x. I went ahead and distributed it out because distributing through an x is easier than using the product rule. You did realize you had to use the product rule right there, right? If you were going to leave it. So what the mean value theorem says, f prime of C equals f of B minus f of A over B minus A, where this is A and this is B. Okay, so f of 1 minus f of negative 1 over 1 minus negative 1. F of 1, if I fill that in, I get, let's see, f of 1 is negative 2. I've already filled these in, so to save time on the video, we're just going to tell you what those are. So I've got negative 2 minus 0 over 1, let's say plus 1. So that's negative 2 over 2, which is negative 1. So f of b minus f of a over b minus a is negative 1. F prime of c, well, f prime of c would be, the derivative of this is 3x squared, but instead of an x, I'm going to put a c, minus 2x, 2c, and that's it. So, ooh, mistake. I didn't distribute my x to my 2, so it would be minus 2. Called it at least. So that, you just set f prime of c equal to f of b minus f of a over b minus a, and you solve it. So you do 3c squared minus 2c minus 2 equals negative 1. It's a quadratic, so you got to get everything on one side. 3c squared minus 2c minus 1 equals 0. That factors, you can S and P, it ends up being 3c plus 1 and c minus 1, which gives me 1 and negative 1/3. This, however, is an end point. Okay, so I'm going to throw it away. You can't include your endpoints because you're saying it says somewhere on the open interval there's a point C on the open interval. Endpoint not included. So yeah, x equals, or C equals negative 1/3. This one we're going to do the same thing. F of b, f of 2 minus f of 0.5 over 2 minus 0.5. F of 2, I already figured this out. Oh, I just wrote it down. This whole thing ends up being negative 1, just to save time. On this one, I would have to do low d high minus high d low over the square of what's below. And I would need to set it equal to negative 1. By the way, it's not differentiable right here because it's not continuous, but it's not continuous at x equals 0, which is not on the interval, so I don't actually have to worry about it, so I'm good to go. So, let's see. If I simplify the top, that's x minus 1 over x squared, which actually ends up being negative 1 over x squared equals negative 1. So I would cross multiply. Negative 1x squared equals negative 1, x squared equals 1, x equals plus or minus 1. But negative 1 is not on the interval, so I throw it away, so C equals 1. And if it asked us to justify why that is, we would say because the mean value theorem guarantees AC in 0.5, the open interval, that the derivative equals the average rate of change. example 3, the figure to the right gives two parts of a graph of a differentiable function from -10 to 4. The derivative is also continuous. Explain why f must have at least one zero in -7, 1. Well, it looks like it's going up. It's going to eventually have to come back down somewhere, and it's going to have to cross through. So in order for it to be continuous, it would have to cross those. And that is the intermediate value theorem. The intermediate value theorem says that because f of -7 is greater than 0 and f of 1 is less than 0, the intermediate value theorem guarantees a value of c in the interval -7, 1 such that f of c equals 0. Explain why there must be at least one point in the interval -7, 1 whose derivative is -5/8. Well, let's try f of -7 minus f of 1 over -7 minus 1. F of -7 is 1, 2, 3, 4, 5, 6, 7, 3. -7, 3. And this is, and then 1, is it -1? 1, -1. So it would be negative, or is that -2? Hold on, I'm struggling. No, that's 1. And, oh, God, I can't, oh my gosh, it's 4. You already figured that out. So it's -1 minus 4 over 1 minus -7, which is -5/8. This is the average rate of change. Let's call it arc average rate of change. And the derivative is the instantaneous rate of change. So the mean value theorem guarantees that f prime of c equals f of b minus f of a over b minus a at least once. Make a possible sketch of the function. Yeah, I've already done that. Good for me. Make a possible sketch below of the function with exactly 2 zeros of f prime. 2 zeros of f prime, oh, down here, would mean there, 2 zeros. Be 2 maxes or 2 mins. Oh, that one has 3. Exactly 2. Oh, crap. That's bad. What if it flattened and then went down? It's called an inflection point. Increasing versus decreasing. It says, why mathematicians feel the need to define everything is a mystery you'll probably never figure out unless you become one. Then for some inexplicable reason you will find yourself questioning the truthfulness of every argument ever made, reducing every argument to its basic foundational vocabulary, and finally analyzing the very soul and fiber of the definitions. With this in mind, we will now define what it means for a function to be increasing and decreasing. Obviously, we cannot just say that a function is increasing when all the function values get bigger. A function is increasing on an interval for any two numbers, x1 and x2, if x1 is less than x2. Implies f, in other words, if it goes like that, it's increasing. It goes like that, it's decreasing. It says, what interval is the function decreasing, increasing, constant? Well, it is decreasing from there to there. So that's actually from 1 to 3. It is constant, so it's decreasing from 1 to 3. It's constant from 3 to 5. And then it's increasing from 5 to 7. It says, what is the value of the derivative when the function is decreasing? When it's decreasing, the derivative is less than 0. When it's increasing, the derivative is greater than 0. When it's constant, the derivative is equal to 0. And these are our, we already talked about this a good bit. That's our justifications for increasing, decreasing, and constant. And that just says this. This is all this says right here. You can read through that at your leisure. Pause me, read, unpause. Find the intervals on which f of x is increasing or decreasing. To find increasing or decreasing, you do it the same way you'd find maxes and mins. You just take the derivative, 3x squared minus 12, set it equal to 0, 3x squared equals 12, divided by 3, divided by 3. X squared equals 4, take the square root, x equals plus or minus 2. Put it on the sign graph. Negative 2, 2, 3x squared minus 12. If I fill in negative 3, I would get 9 times 3 is 27 minus 12, that's a positive. If I fill in 0, I would get negative 12, which is a negative. If I fill in 3, I would get a negative 3 again, which is positive. I mean, not negative 3. I'd get a positive number. Fill it in. So it's positive, negative, positive. So where is it increasing? And this is my graph of f prime. It's increasing from negative infinity, negative infinity to negative 2, and from 2 to infinity. Why? Because the derivative is greater than 0. Okay? Where the derivative is less than 0, it is decreasing. And that is between negative 2 and 2. And your justification is this. You don't just say it. You can't say it's greater than 0, it's less than 0. You have to say the derivative is greater than 0. The derivative is less than 0. Alright, let's do this one. This one's a little bit harder. F prime of x equals 2/3 x squared minus 9 to the negative 2/3 times 2x. So if I simplify it down before I try to set it equal to 0, I would get 2 times 2 is 4x over 3 times x squared minus 9 to the 2/3, which is the same as 4x over 3 times the cube root of, I'm stupid, that should not be a negative 2/3. I just realized my mistake. I didn't mean to erase all that. I want a little eraser. Sorry about that. It should be a negative 1. You probably realized it. Hopefully you did. 1, negative, oh, positive, negative 1. So of x squared minus 9. So remember you set it the top and the bottom equal to 0, and the x squared minus 9 equals 0, because if you set the whole thing equal to 0, then you divide 0 by 3, you get 0. You cube 0, you still get 0. So x is 0 and x is plus or minus 3, because that's x plus 3, x minus 3. So I'm going to do my sign graph. X, or 4x, x plus 3, x minus 3. And I've got negative 3, 0, and 3. Let's see, negative, negative, positive, positive, negative, negative, positive, positive, negative, 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 positive. So negative, 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 positive? No, that's wrong. What did I, oh. There. Now it's better. Positive. Negative, positive, negative, positive. So it is decreasing from negative infinity, whoops, negative infinity to negative 3, and from 0 to 3, because the derivative is less than 0, and it's increasing from negative 3, 0, u, 3 to infinity, because the derivative is greater than 0. And we're actually not going to do this yet. We're going to save anti-differentiation. No, we're not. We're going to go through it really fast. So suppose you were told that f prime of x, the derivative was 2x minus 1. What could f of x possibly be? Think about it for a second. Pause, think. Okay. And we're back. How about x squared minus 1x? Because if you took the derivative of that, you would do 2 times x is 2x, and then minus 1. But what if I had like plus 4? Would that give me 2x minus 1? What if I had plus 7? Also 2x minus 1. Plus 8? Plus a million? Still going to give me 2x minus 1. So what you have to do this is called taking an antiderivative, is x squared minus 1x plus c. It's plus a constant. Plus a constant. And then that's actually where we're going to stop. Just a little introduction to antiderivatives. Sorry if that was too long.